All right, welcome to our second workshop for embedded program gym. And the topic of today is geometry. So CP Gym is a workshop series where each week we'll learn a new algorithm through a short lecture, and then we'll compete in a friendly contest in teams of 2 to 3 people. The competition will consist of a full set of problems and also some problems related to the new algorithm that we just learned about. And after each session, solutions will be available via this link at the UCLA ICPC Gitbook. So if you need to check your solution or see what the correct solution was, you can follow this link and read the editorial. All right, so now let's move on to our topic of today, geometry. We'll start by introducing some basic concepts of geometry, computational geometry in C++, and then we'll move on to a more advanced topic by finding convex hull. Okay, so I guess the easiest problem to program is to find an equation of line given 2 points. Can someone on the top of their head tell me what the equation of what a slope would be for this line? Anyone? Yeah.
I think it's B minus B divided by A minus C.
Yeah, that's correct. So basically, you can do the very simple computation, find the slope and the second term. And essentially, if you need to find a slope of a line, you just accept 4 numbers, which are the coordinates in 2D plane, and then you can output another pair of numbers, which would be the terms in your equation. So this was pretty easy. Now, another concept that we need to know in geometry is dot product. So can anyone tell me what the formula via coordinates would be if you're given 2 vectors in 2D plane? What would be the formula for dot product? Alternate? Yeah.
X1, X2 plus Y1, Y2.
Exactly. Yeah, so this is also pretty easy. Essentially, you need to multiply the first terms and the second terms, and very easy C++ function that can find the dot product for you is essentially copying down the formula and returning the result. This can be extended for multiple dimensions, for high dimensions, 3-dimension, more. So any questions so far? Okay, this was pretty easy. Next thing is a bit more complicated. It's cross product. So can someone tell me what would the cross product be for these 2 vectors, or how would you find it if not the formula? Yeah.
I think it's y2z1 minus y1z2 in the first coordinate. It's like with each coordinate, you take the other 2 and do the
right. Yep, exactly. So you to find it, you can basically build a matrix with the first row with unit vectors, and then the second and third row with the coordinates of the vectors. And this is what we will get eventually. So in C++, again, you can basically output these 3 numbers corresponding to each coordinate. This is going to be a pretty useful technique for future computations, as we'll see. So this was the cross product. Next one, next important concept that we need to know for 2D computational geometry is area. So let's start with a simple one. Can someone tell me if they can find the area below the line segment if you're given 2 points, x1, y1, x2, y2? It's essentially an area of a right trapezoid below it. Does anyone know the formula for that? Yes?
1/2 the basis, which is y1, y2.
Okay.
And then
No, 1/2 of their sum, right?
yes, after sum and then times the A, which is y2. Oh, that was
Yeah, the height would be
Any
x2
extra
minus
one.
x1, right? Yeah. No worries. Exactly. So basically, you multiply the sum of the heights by the the sum of the bases by the heights and divide it over 2. So that would be the area. Notice that in this case, we're talking about signed area. So if we are trying to find area via this formula, you can notice that, for example, if the second point was to the left of the right point, the area would be negative. So essentially, by computing this value, we can not only find the value of the area, but also deduce some information about configuration of those points in the plane, which will be very useful when we move on to higher number of points, like triangle or polygons. Okay, so let's move on to the area of triangle. So if we only take into account what we just learned, the area of trapezoid, can someone suggest a method to find the area of a triangle only using the concept that we just learned? There's, I guess there's even a slight hint on the picture here. So let's say we only know how to compute area of a right trapezoid. Can someone say what the area of a triangle would be? Yep.
Like there's 3 trapezoids in the diagram, and you add up 2 of them, so
Yeah, exactly. So essentially, if you only know how to compute the area of trapezoid, you can add the area of the left trapezoid plus the right trapezoid, and then subtract the area of the bottom trapezoid. So this is exactly what we do. And essentially, as I just said, because we are considering the signed area, we can basically sum up the signed area. And as you will see, the third term will be negative since, like in the previous example, the second point lies to the left of the right point. So this is equivalent to subtraction of that area. Okay, and obviously that's pretty easy to put into code. You simply copy down the formula and output the result. Any questions so far? So as you will see, this formula, this area is actually very important to the next concept that we are going to talk about, which is the orientation of 3 ordered points in plane. Oh, and by the way, the area that I just talked about, that concept of adding up and subtracting trapezoids can be extended to any number of points. So if you have a convex polygon in the plane, you can do exactly the same by summing up the signed area of trapezoids over each consequent pair of points in the polygon. But moving on to the orientation of 3 ordered points, as we'll see in this example, depending on what the order of the points in triangle we are considering, the formula that we just talked about will give us the same result, but with a different sign. So notice if we are going in a clockwise direction, we'll add the first small trapezoid, the second one, and subtract the third one, which leaves us with a positive area. But if we are going in a different direction, ACB, for example, which is counterclockwise, we'll add the big trapezoid first, subtract the right one, the left one, and this leaves us with a negative area. So this gives us a hint on how we might want to deduce the orientation of 3 points in a plane based on computing that area or some value related to that area. So essentially, by computing that value, we can deduce if the points are ordered clockwise or counterclockwise. We don't have to divide by 2 necessarily, but as we will notice that if the area is negative, which is the second case, the points are oriented counterclockwise. So the function that's in the example here, which returns true if it's counterclockwise and false if it's clockwise, will return true and false in other case. Any questions so far? All right. So one final introductory concept that can be useful. We are not going to talk more about it today, but something that is good to know is how to compute a distance from a point to a line. And here we can utilize the concept of area that we just learned. So as we know, the area of triangle can be computed by multiplying the height and base and dividing by 2. So by using that formula, we can find the height of the triangle, which is essentially the distance from a point to the line segment. Does anyone have questions about this? So just once again, if we are given a point C and we want to find the distance to the line defined by points A and B, we can compute the area of a triangle that's formed by these 3 points and then divide it by the length of the base and multiply by 2. Essentially computing the area in 2 different ways and solving the system of that equations. Okay, so once we know this, this was the introductory concepts. Now let's move on to the more advanced concept of convex hull. So the problem statement is as follows. Given endpoints in a 2D plane, you want to find the convex hull. I'll define it later, which is, or in other words, a set of points that form a convex hull. So a convex hull, by definition, is a set of points that's defined by a smallest polygon that can encompass all given points. So, for example, in this picture, you're given a set of red points, and the convex hull is going to be this set of points that forms, if you connect them, that forms a polygon, so that every other point is inside that polygon. Does anyone have questions about the definition of the problem, what you're trying to achieve? And by the way, each point is going to be defined by a pair of coordinates in 2D plane. Okay, so there are actually many algorithms. There are several algorithms to find the convex hull, and today we're going to talk about the easiest or the more the most common one, which is the following one. So what we need to do is to find the leftmost point out of the all coordinates, which is out of the all points, which is pretty easy. We just need to find the smallest number in the 1D array of x coordinates. And the next step is a bit more complicated. We need to iteratively find the next point in the hull, starting from that point. So the idea is that once we find the leftmost point, we are pretty much sure that it's going to be in the convex hull, because there's nothing to the left of it. So there's no way to draw that polygon without that point. So we know if, for example, here x1 is the leftmost point, it is going to be in the convex hull. So our next step would be some kind of wrapping. The algorithm is also called wrapping algorithm. Essentially, you find x2, then you find x3, x4, and repeat the steps that I'm going to talk about later until you end up in the point that you started with. So at every iteration of the algorithm, you need to find the next vertex. So you need to find the next vertex Q of a vertex P. It turns out that that next vertex is the rightmost vertex that you see if you stand at point P. So for example, if you stand at point x3 and you're looking at other vertices, then the x4 is going to be the rightmost. And it turns out that it's also part of the convex hull. If you repeat that procedure several times, so you go to x2, you start with x1, you see that the x2 is the rightmost, you add it, then you add x3, x4, x5, and so on. You will eventually get the convex hull. So I believe the first step of the algorithm is pretty basic. So the main question is, how would you find the rightmost point? Well, let's solve the easier problem first. Imagine you're given an 1D array of integers and you want to find the largest element in that array. Well, can someone describe what their approach would be? You just need to find the largest integer in an array. How would you do that? Anyone?
You can just loop through the array and find it.
Exactly, right? So in more detail, basically you set the result to the first element of the array and then linearly traverse it. And every time every time the current element's value is larger than the value of the result, you update the result and you end up with the largest value in the array. So the comparison operation that you perform each iteration of the loop is some kind of integer comparison, maybe greater than, less than or equal, depending on the question in the problem. So we can actually use the same approach for finding the rightmost point in an array of 2D coordinates. If we are standing at a different point, let's call it previous point, because we are going to do that iteratively. So imagine you're standing at previous point, you're given endpoints with in the plane, and you want to find the rightmost one. So essentially, you do the same thing. You set the result to the first point, whatever the ordering might be, it doesn't matter. Then you linearly traverse the array and update the result to the current element, to the current point we're considering, if the points, previous point, current point, and the result are ordered counterclockwise. So here, the comparison operation is actually the function that we just discussed, the counterclockwise, which will return true if points A, B, C are ordered counterclockwise, and false if they're ordered clockwise. So it might be a bit difficult to grasp why exactly this would lead to the correct result. So let's look at an example. So imagine this is the stage of our algorithm. We've already found 3 points of the convex spool, x1, x2, x3, and now we want to find the next point. So we know, even just by looking at it, that the next point is going to be A5. So that's what we want to do. Let's say they are ordered in some way, A1, A2, A3, up to A7. There's no particular ordering to the points. So we start from the first one. So the current element is A1. Yeah, so the current element is A1, and the result so far is also A1. We said the first point. So the first step we do is we compare, we find the result of if the x3, A2, A1 are ordered in a counterclockwise direction. So basically, the result is A1 so far, right? This is the third input. The previous point is x3, the point we're looking at, we're standing at, and then the current element is the next element in the array, whatever ordering it might have. So we compare, we find the ordering x3, A2, A1. It's ordered in a counterclockwise direction, so that would return true. So we update our result. I guess the naming is not great, but par is the result. We update it to A2. I guess you can say it's current value of the result. Now it's A2. So can someone tell me what would be the next 3 inputs to the function? What will we do in the next iteration? So we have our previous point. The first input stays the same, x3, because that's where we are standing at. Then the next one is the next point in the array we are considering, which turns out to be A3, just by the order. And then the resulting value, which we think is the rightmost so far, is car A2. So we'll have X3, A3, A2. So X3, A3, A2, that's again counterclockwise. So as you can see, we are kind of, by doing this thing, we are kind of moving to the right every time. Yes, question?
So how are the points ordered again?
There's no particular order. So you just read the input and you don't have to order them. So imagine you read the input in order like this.
Just like in A1.
Yeah. Order is just 1, 2, 3, 4, 5, 6, 7. So now you see that these points are again ordered counterclockwise. So you update the result, which is now A2, you update it to A3. So anyone can tell me the next input? Yep, X3, A4, A3. And here, X3, A4, A3, they're actually ordered, they're actually ordered clockwise. So by the algorithm, we do not update the current element. So it stays A3. We move on to the next one, which is A5. So we see X3, A5, A3, X3, A5, A3. And remember, this is going to be our result, if it's all correct. So they're ordered counterclockwise, so you update the result to A5. I didn't write the next steps, but essentially what you would do, you would consider A6, you would say X3, A6, A5, they are ordered clockwise, so you don't update it. And then X3, A7, A5, and again, they're ordered clockwise, so you don't update it again. And you end up with the result of A5, which is what we expected it to be. On a conceptual level, you can think of it as if you're considering 3 points, and the ordering is clockwise, and this is your result, the middle point. Essentially, the last point in the input is more to the right than your current result. So it makes sense to update it to the new point, just like we did here. We saw that or I guess it would be easier to say if you are seeing that the 3 points are ordered counterclockwise and your current result is the last point you're seeing, then the middle point is obviously to the right of the last point. So it makes sense to update the result to the middle point. Okay, any questions for the algorithm? I guess to give more visual understanding of what's happening, essentially what I was talking about at the very first slide of the algorithm is this big picture. So once again, you find the leftmost point, then you find the rightmost point starting from this point. You add it to the convex spool. Then you do the same procedure for that one. You find the rightmost point standing at this point. You add it to the convex spool, and then repeat that algorithm until you end up in the same point that you started with. So that's the entire algorithm. Here I have just a short pseudocode of how it works. Essentially, that's what I just said. You set the first loop is just to find the leftmost point. You just traverse it linearly. You find the leftmost point, and then until you get to that point again here, you find the next point in the convex spool Q. I guess I forgot to set P to Q. So after here, you add Q to convex spool, and then you set P to Q. So P is always the previous point. You set it to the Q, and then you just repeat the algorithm that we just discussed over and over again. We go through all points, find the rightmost, add it to the convex tool, and do it again and again. So can someone tell me what the time complexity of this algorithm is going to be? Right, so it seems like it's going to be n squared, and that's a pretty good estimate. Essentially, we do have like two loops. The inner loop considers all points, all endpoints, and the outer loop seems to consider all points. But you can actually improve the estimate to be n times the size of the convex spool, n times m. And it turns out that in most cases, the size of the convex spool is much smaller than the number of points we have. So if we only have 3 points, obviously, then the size of the convex spool is the number of points. But if we do have like 100 points, there's high chance that the convex spool is going to be much, much less than 100. So both estimates are valid, but in most cases, it is faster than n squared. So it's pretty efficient algorithm. Okay, any last minute questions about anything I've talked about today? Yes?
So would it be like, I'm assuming if you have a random like distribution of points, then the amount of points on in the convex hull would be like around square root of them?
Like that's
I'm just like guessing, because it would be kind of the case about if it's like a square or a circle, you know?
right, that makes sense. Yeah, I actually don't know what the distribution would be. I guess it could be even smaller than square root of n. Well, yeah, if you think of it as an area, right? If it's just a circle, so the points, all points you have is the area of the circle, and then the pool is the length of the perimeter. So in that sense, it is of order of square root.
Yeah.
But it's very rough estimate. Sorry?
The previous slide.
Previous slide. Okay.
So, I'm a bit confused. So are you saying that if the previous point in the complex hull appears twice with the counter complex function, then you will update to the next point? I'm not sure how you update next one, not next to the X4.
Okay, so once we find x4, we now set the previous point to x4, and then consider all other points.
So to find X4, what's the combination for X?
Sorry, can you repeat the question?
What was X3? How do you update to X4? Do you have to iterate over all points?
Yeah, so we iterate all the all points. So for every point that's not x4, we iterate for all other points, and then among all other points, we find the rightmost of all. So if this is x4, which is our previous point, then we look at all other points and find the rightmost out of them. That's going to be x5, and then we add it to the convex spool, and now we just repeat what we just did for x5.
Okay.
Okay, there are no more questions. Let's put what we learned into practice.